Okay, we're still working on the polar amino acids, and what I'd like to do at this point is switch to the left side of the page and talk about those that are polar charged. And there's only 5 amino acids left, and I'd like to start at the bottom of the page. So the reason I want to do that is because the 2 that are down here, we call them polar charged negative, because their side chains are typically negative. And what we have here is 2 amino acids that are parallel to 2 that we covered on the polar neutral. You can see I filled in the notes again there for asparagine and glutamine on the right-hand side of the page, and those have amides. And on the left-hand side of the page, we have 2 parallel amino acids, aspartate and glutamate. The names are similar, their structures are similar. The difference is they have a carboxylic acid, or actually, we should make a note that it's a carboxylate. These are carboxylic acids which have pKa's in the 2 to 5 range, so therefore, at a neutral pH, we would expect that they would be negatively charged, and that is what they are. Sometimes they're called acidic groups in textbooks, but that's not really a good way to refer to them because they're actually existing as the conjugate bases, not the acid form typically. So we think of these 4 as a group. Asparagine and glutamine are the amide versions of aspartate and glutamate. We can say that these are good for H-bond acceptor, not donor on the side chain, but acceptor they can be. They're tremendously good for water solubility because a full charge is always more polar and therefore more water soluble than neutral. And lastly, we have a new feature here. These can form ionic interactions with positive charges. You might be able to interact, say, with a positive charge like a sodium ion or a calcium ion, or maybe with a protonated amine that has a positive charge. So we're very interested not just in the structure, but also in the properties and functionalities that these amino acids have. So to finish this off, we simply go to the last 3 up here, which are the polar charged positive, and those are going to be the last 3. Now, in some ways, these are some of the most difficult ones for us to deal with. Not so much lysine. Lysine's pretty easy. What you can see is it has a alpha carbon, a beta carbon, gamma, and then there's a 4th and a 5th carbon. We call it delta and an epsilon, and then an amine group attached out there. So that amine is like any other amine. It has a pKa in the 8 to 11 range. And what that means is that it's typically going to be protonated and positively charged. So, what do we know about these? These are going to be great H-bond donors, not acceptors, because they don't have a free pair of electrons on there. They're also going to give us great water solubility. Like we said at the bottom of the page, a full charge is always going to be even more polar and therefore more water soluble. And lastly, these are going to have great ionic interactions, this time with negative charges. That might be a negative chloride ion or a phosphate ion, or maybe even a carboxylate from another amino acid. So that the 3 things we talked about here, that's true for all 3 of the polar charged positive residues that we have listed here. We have lysine and histidine and arginine. These are some of the hardest for us to work with because they are very difficult to draw, some of them. Lysine's not too bad here, but I want to emphasize to you that the protonated side chain of lysine is typically positively charged, but it can give up its proton at very high pH, maybe if you're up to 11 or 12, and it's going to be a deprotonated amine like we have shown here. And that's one of the challenges we have here. It's important for you to know the structure of lysine, but you also have to know the structure of it deprotonated. That's true of histidine as well. Histidine can be protonated positive or it can be deprotonated in neutral. Same with arginine. Arginine has an NH2 positive, but it can deprotonate if you get very high pH and be NH and neutral. It's one of the real challenges of understanding these amino acids. So let's take a look at histidine. Histidine is going to have a complex, difficult to draw structure. It has a beta carbon, which is coming off the alpha carbon, and that's shown right here. And then it has a ring structure, and that is one of the hardest things to be able to draw. It has 2 double bonds and 2 nitrogens. We call this, by the way, an imidazole group. You don't need to know that name, but I do put it out there just in case you see it in your reading. So here's one little hint about dealing with the deprotonation of these types of nitrogens. The NH plus that's going to lose the proton is always attached to a double bond, and we can lose that proton and it becomes N with a pair of electrons and neutral. It's a common mistake for people to try to take the NH or the proton off the NH, which is attached to a single bond, and that will not work. This is also going to be true in arginine. The proton you can lose is the NH2 plus that's attached to a double bond. You can lose that proton and become neutral, but you cannot take the proton off either of the other 2 nitrogens. They would then become negatively charged, and that's just not going to work. So arginine has 3 carbons and then a 4 atom group out here. We call that a guanidium. Carbon in the central, 3 nitrogens around. Again, you don't need to know the name of that, but I would like you to be familiar with the structure, and I put the name out there just in case it shows up in your reading. Okay, that's the 20 amino acids, and we'll leave it at that for now.